look at study session 3. Now in study session 3, we want to look at mathematical analysis of basic theories of economics and also look at the total and the partial derivatives. So in economics, derivatives are a bit different from derivatives when we talk about derivatives in the financial sector or in the finance. Because in finance, there are certain stocks or certain financial instruments that are used that are called derivatives. But in economics, we are looking at it from the calculus point of view, where we talk about how to derive the differentiation from any of these formulas we will see when we go ahead. So we also look at total derivatives and then also look at partial derivatives. So so this takes us to the next slide here, where we have derivatives. So the derivative dy dx can as well be expressed as a ratio of differentials, where dy is the differential of y and the x is the differential of what? X. So suppose we have a model of one exogenous parameter variable. So what we mean by exogenous is just simply a variable that affects or influences a particular function outside the dependent variable. So outside the model. So you can as well, have this function where y is equal to f of x. Then the differential of y is basically the dy. And it is measured as a rate of change in y as a result of a small change in x. Because when there's a small change in x, it impacts on y because y depends on x in that particular function. So when there's a small differential, or when there's a differential in y, it will also measure up by a small increase or change, either increase or decrease of x as it impacts on the y variable in that function. So differentials as a mathematical method as some fundamental characteristics will help us to understand the operations better. So there are a few characteristics that we need to know that will help us in differential of some of these derivatives. So the number one thing here is that in differentials, y dy is an exogenous variable in this equation. Dx is an exogenous variable. So dy is an endogenous variable, y dx is an exogenous variable. Now, in this instance, dy is dependent on x. So what we mean by this is that the changes in x affect y, and y depends on x to change. So if x does not change, y remains the same. So that's what we are saying here. So the second thing to note here is that since the y is dependent on the x, it therefore means that if the x is 0, then the y must also be 0. That is very, very important to note. So, but when the x 0, we then divide the y by the x to obtain f of x. Now, whenever you see in a note, maybe textbook, slides, or note, or whatever, where you have f with an apostrophe on it, it's simply saying that that function has been differentiated. So the f with this apostrophe x here is just simply saying that this is a dy dx of that function. So then we have the third one as the differential dy can only be expressed in the terms of other differentials, like the x. So it depends on x to change. Now, there's what we call total derivatives. So total derivatives has to do with the total of both the endogenous and the exogenous variable within a function. Like if you see here, you see that yq is equal to g of pi and I is equal to h of p. So these are addition of these two will give you what we call the total derivatives. That's why you say the total derivative measures the direct effect of P on Q plus the indirect difference of P on Q through I. So, in a nutshell, we'll have what? QP plus QI. Now, for example, the question says find the total derivative of the Q dp given the function Q equals to F. So, now they've given us a function of Q equals to F of Pi, which is equals to 12P raised to the power 3 plus 14I, where I is G of P is equals to what? 8P raised to the power 2 plus 6P plus 16. Now, for the solution of this, we will apply the total derivative methodology to solve this problem. Therefore, the total derivative of the Q dp with respect to P in this equation will be the Q dp is equals to dp plus dj into ai over the I over dp. Now, when we take derivative of that particular function, this one, you see that using the differential rule, you see that when we do that, we have 36p squared, and then qi is equal to 14 from this differential, and then we also have that the I dp is equal to 16p from this differential, and then when we substitute this now into the model, then you see that we'll have this resulting value 36p squared plus 224p plus 84. So as a check, we can substitute the function of g into the function of f to get the resulting value. So this is just mere substitution, where we take this 14i and put the 14 here, and then substitute it with I, and then in this one we have our 12p3. So 12p3 plus 14i, which is the first equation, is 8p squared plus 6p plus 16, which was what we got from our previous equation as I. So just a mere substitution into that and then expand it will now give us what? It will now give us 14 times 8p squared will give you 112p squared plus 12p cubed times 16 will give you 84p. So then you have plus 264 when you multiply 14 by 16. So that will give you 224. And then when you expand that, you arrive at this answer when you take the Q dp of this equation. Meaning that the Q dp means when you differentiate, it means that 3 times 12, which is 36, p raised to the power 2, and then 2 times 112, yeah, raised to the power 2p, so it will give you p and then plus 84. Then the constant, differential of the constants, remember, is always equals to 0. So this is the final answer from the total derivative. Now, while we have the total derivative, there's also what we call the partial derivatives. Now, partial derivatives are just functions of several variables and its derivative with respect to those variables with holding other variables constant in a particular function. So the introductory analysis is just the partial derivative of a single variable, and it is why moving to the analysis of a more than one variable, because in you're dealing with variables or with models, you find out that making use of equations or models that are having more than one variable, which sometimes we call them a multiple regression model. So now here we have an example. We say, for example, given the polynomial in variable x and y, that is to say, f of x, y is equal to a x raised to the power 2 plus by raised to the power 2. So the partial derivative with respect to x in this equation is written as the f of x y over dx. So the x of sy over the x means that when we differentiate in this equation, we are only differentiating with respect to x and not y. And when you do that, it means that this becomes 0 because we are not interested in y, and then we just have 2ax. That's why we are having 2ax with respect to the x. Now, when we take the partial derivative with respect to y, then we are no more interested in the x variable, but only with the variable with y. So, in this case, when we differentiate this, it means that we have 2by, because when you 2 minus 1 raised to the power will just give us y, which is not visible in the equation. Remember, we did that in the first year. Okay, so the problem with functions of more than one variable is that there is more than one variable issue here. So in other words, what we do, or what do we do if we want only the variables to change? So for instance, if we want only one variable to change, what do we do? So for instance, one variable could be changing faster than the other variables in the function. So for more detail on this, refer to the study material for a more reading. So basically that's what partial derivatives and total derivatives are all about.